All right, it's time for us to get started. First, a very quick announcement. We do not have class on Monday. Nobody has class on Monday. Don't show up on Monday. You will be lonely. So long weekend, long cold weekend. I will see you all on Tuesday, not Monday. Don't freeze yourselves to death. Let's see, what else? We have something due in here tonight. It's the world's most challenging assignment. Quiz, exam, whatever you want to call it. It's essentially, I called it a one-word essay. So get that submitted, get your GitHub username submitted so that I can add you to a repository that we're going to make for you to submit all of your work this quarter. We have a very slow start to this quarter, which is good, meaning that I think on the syllabus, I had something due next week, and there may still be something due next week, but it will be some very basic stuff as we get up to speed. I've changed how some of the content of the course and the ordering of it so that we don't really have a lot to do labs on for the first couple of weeks. So that means that it's okay that it takes a little while for us to get started with that process. Today, we're going to finish the single last review slide, and then I don't want to get too deep into a new topic. We'll wait for next week to do that. So we will do a Project Euler problem or two with the time that we have left. Any questions or concerns about anything discussed so far? All right. That last topic that we're going to be talking about is APIs. To what extent have we used APIs in the past or know what an API is?
Application project interface.
Application programming interface, very close, but yes. So what is it and what is it? Yeah.
It's how programs talk to each other.
Okay, how programs talk to each other. That's a good start.
I'll say like it's something that can be interacted with.
Yes.
So you can look into it and grab information and pull it out.
Yes. So the way that I like to think about it is, as humans, there's a lot more to us and who we are than just our public face. You know, I have some work-life balance. Some stuff goes on at home that nobody wants to hear about or cares about at a professional level. And similarly, when you write some code, there's going to be some of that that is privately facing, that is stuff that you are aware of as you implemented it, and some stuff that's going to be publicly facing that are tools that other developers can use to interact with your content. We talked about similarly how you don't necessarily know all of the details about how a scanner works, but you know the methods that you can call with a scanner and the result of those method calls. All of those are documented in an API. So it's a documentation about how to use code, and it has nothing to do with how that code is implemented. So application programming interface. The Java API, for instance, gives you a list of every class and method that comes with the Java programming language. One of those objects is the scanner, one of those objects is the string, things that you have used before. But as you start writing more complicated programs and start designing tools for use by other people, you will also be writing the API for the code that you write, which means that what do other people need to know in order to interface with your code? So the first one you usually see is the Java API. Tells you how to use all the built-in Java tools like scanner, like file, like iterator, like null pointer exception. All of these are classes that come with the Java language. Anything you've ever imported from any Java library is part of this. And we talked before about the separation between use and implementation. The example that I used is you don't need to know everything that happens underneath the hood of your car in order to operate your car. So in this class, there will be labs, and those labs will come with APIs. Is this something that you've seen before in 210 or 211? And then you kind of program to the API. I tell you what the publicly facing methods need to be. And that way you go implement it and I can test via those tools, the methods that you write, whether or not your implementation is correct. There's a lot more to APIs about designing your own APIs, what's a good idea, what you really need to be thinking about when you design an API. We'll have that discussion in software engineering for the most part, but the most important piece of that is that you need to think about your API at the very beginning of a project, because this is not something that is easily modified. You can extend an API very easily, but why might it be a problem if you modified your own API? Any intuition?
Customers that may already be using it won't be aware of the updates for it, or won't know how to use it.
Yeah, if what happens? Let's say that I tell you that there's a method that you can use in this great program that I have written that allows you to change your GPA to a 4.0. And then you go write some code that interfaces with that and it works. And at any point you can update your GPA to a 4.0. And then I remove that functionality and you try to go run your program. What happens to your program? Yeah, it crashes because it doesn't have that support anymore. You go to import that code and that code has changed to the point where you can't interface with it anymore. It's the same where if I have a method that takes one parameter and I go change it to take 2 parameters, what happens? When someone tries to use it, it crashes because their code that they're using still only passes 1 parameter, but now that method expects 2 parameters instead. So you can see how changing the API is really bad. If Java changed how the scanner works, it would break most of the programs you had written up to this point. You wouldn't be able to compile and run your programs anymore. You got to show them, you wake up one day for a coding interview and you go in and you show them this really cool project that you've done. You go run it and it breaks. This actually happened with the C++ libraries back in the day, and now they're a bit better about it, but this actually happened to me, where I went to go run a program that wasn't even 2 years old, and it broke, and I had to go figure out what about the C++ API had changed such that my program would compile and run. I hated that. It made me a very bitter person for a while. It took me a while to code in C++ again. I just abandoned the language for a good few years. It's just not something you recover from very easily. So you need to design the API from the beginning in a way that is extendable but not modifiable. So we'll talk much more about that in software engineering, but that's something that I think helps people to understand what an API is. It's kind of a bond that you make with people who are using your code that says, here are all these tools. They're not going to change. You can continue to use them from now until the end of the world. It's great. Questions about APIs? Again, you'll see what that looks like when I give you an API for a lab, and then you will program to that API so that you have the functionality, so that if the API declares that there's a method that does these things, you will go implement the logic so that there is a method in your code that does those things. All right, that's it for the review. This is most of what I expect that people know coming into this class. So hopefully your prior classes paired with some of the stuff that we've gone over, you feel caught up and that most of these topics make good intuitive sense. If that's not the case, let me know and I can circle back as we have some time to try to make any of these ideas clearer, flesh them out a bit better. But the next best thing to do, I think, is going to be to go and tackle a couple more programming problems, because these abstract ideas are all great, but what is an abstract idea without your having the opportunity to go implement it and solve some problems that use them? So we are going to go do that. On our first day of class, we solved the first Project Euler problem. We're gonna hit up the second one. All right. Who's familiar with what a Fibonacci number is, or the Fibonacci sequence? We've seen it before, maybe in 211. What was the context for how you've seen it? For those of you who have. It's a very common recursion problem. Yes, absolutely. And one thing that's fun about recursion is recursion and iteration are kind of synonymous. Any problem you can solve with recursion, you can solve with iteration and vice versa. So the way that you implement this problem could be iteratively with a loop. It could be recursively with a function that calls itself. So I challenge you, if you have not implemented this recursively, that's a pretty good challenge for understanding recursion. So this question says, each new term of the Fibonacci sequence is defined to be adding the previous two terms. So we will hard define the first two terms as 1 and 2. It's usually either 0 and 1 or 1 and 1, but in this case, we're going to define the first two terms as 1 and 2. What we care about is the terms that are even. That's not the index that's even, but it's to the terms themselves that are even. So the 1 is not even, 2 is even, 3 is not even, 5 is not even, 8 is even, 13 is not even, 21 is not even, 34 is even. Maybe there's a pattern there. Maybe that pattern continues. Maybe it doesn't. We don't really know without going through some kind of mathematical logic to try to figure that out. But we're going to add all of the even Fibonacci numbers that are less than 4 million, less than or equal to 4 million. So we need to be able to continuously generate more and more and more Fibonacci numbers until the Fibonacci numbers that we generate are in excess of 4 million, adding up any of the terms that happen to be even. So try to solve this two ways. Try to solve it iteratively and try to solve it recursively. So we'll take some time. Talk to your neighbor. We talked about pair programming on the first day. Reintroduce yourself. Maybe if you're sitting at the same place, if you're not, get to know somebody new, that's fine too. And let's see if we can solve this. In a few minutes, we'll start going over how to get started, in case you're stuck there.
Wow.
Oh, we didn't.
That's right.
Files.
Is everyone clear on what the problem is asking? What variables do we need to solve this problem? What do we need to keep track of?
The previous and the current
Yeah, we're gonna need some previous and current values. What variable types are those?
ints.
Because if we're trying to figure out what a Fibonacci number, the next Fibonacci is, we're gonna take the previous two, which is gonna be the current and the previous, and that will help us generate the new one. And then we just need a way to update the previous and current based on, it's gonna kind of be a window as we move along. What else do we need?
The sum.
Is that going to be an int?
Yeah.
Is there anything else we need?
Temp variable.
Some kind of temporary? I'm actually not sure we do. But maybe we want one. I will leave it up to you to determine whether or not we want some kind of temporary variable here. Maybe it's useful. I'll stop there for now, and we'll see if you can take this idea, run with it, and come up with, we'll start with an iterative solution, because I think most people think more naturally in an iterative sense. So think about what initial values do these things have? And then how do you update them iteratively? And then how do you know when you're done? Let's try not to hard code the 4 million. So we're going to bring that out somehow, and we're going to use that as some kind of static final variable. So we've seen these class constants before. Given our lecture yesterday, does it make sense why a class constant is static? Who could explain why a class constant should be static or why that makes sense?
So that can't be changed.
That's the keyword final. The final makes sure that this does not change, but static is doing something slightly different.
For any of the class objects, they're all referencing the fact that 4 million is the threshold.
Yes, so if we think about the memory usage of our program, since everything in Java is an object, even if we're just making some kind of procedural logic to do this, if we were to instantiate objects of this driver class, which you could do, the fact that it's static says we're going to have one place in memory where we're going to store the number 4 million. And then any instantiation of this, there's just gonna be one reference point. So we would always point to this singular value rather than duplicating it for every instantiation of this object. And that saves you the size of an integer. Does anyone know offhand how many bytes an integer takes? The answer is either 4 or 8, depending on your architecture. If you have a 32-bit architecture, it takes 4 bytes. If you have a 64-bit architecture, it takes 8 bytes. Random piece of knowledge. Anyone think they have a solution yet? Anyone feel like they are stuck? All right, I will give people more time. If we don't have a solution and we're not stuck, we need more time. Got it? Nice.
As a function.
Are you?
While there's other than.
I don't know.
Just go ahead with the regional sub.
I'll do it.
It's a lot easier. What Java did. This.
Yes.
Yeah.
Yes, it is.
So it's just.
I had like, I
iterating,
think it's like
until.
4 lines of code shorter.
Okay.
With the Java.
Yeah.
I think I got it. Very good.
Excellent. Excellent. All right, what should the initial values of these variables be?
We have 0 or 1.
If we're going by the regular Fibonacci sequence, the way that I know it and you probably know it, they should be 0 and 1. According to this problem, the first two Fibonacci numbers are 1 and 2, which makes sense since 0 is going to be even anyway, anything plus 0 is going to be itself. So it actually doesn't matter whether we start with 0, 1 or 1, 1 or 1, 2, they will give you the same answer. But the idea is that we want to figure out what the first and second Fibonacci numbers are, and we're going to store those into previous and current. So they should start out at 1, they should start out at 2. What should sum start out at?
0.
0? That makes sense. Until we've identified an even Fibonacci number, we want to start out the total of all the even Fibonacci numbers that we've seen so far at 0, since we haven't seen any. And then we won't quite worry about temp quite yet. We'll see if we need to come back and initialize this to a value depending on how we want to solve the problem. So logically, what's the first thing we should do?
Make the Fibonacci sequence, or at least make a way for us to get the Fibonacci sequence.
Okay, we want some way of generating maybe the next Fibonacci number
Yeah.
from the current Fibonacci, the last two that we've seen. So we can embed this inside of some kind of loop, probably, where we want to, while we haven't reached the threshold, generate the next Fibonacci number. So what would that look like? Want to help me with the syntax?
You could do while cur is less than threshold.
Values do not exceed. Does that mean 4 million should be counted? Yes or no? Yes? It's probably very unlikely that 4 million happens to be precisely a Fibonacci number that is even. It is even, so if it is a Fibonacci number, we would include it. But if we're going to abstract this code a little bit to where we want to be able to change the threshold, to be able to say whose values do not exceed X or some variable, then we want to make sure that if the threshold happens to be an even Fibonacci number, then we include it. All right, inside of this while loop, what do we want to do? Let's start out, rather than talking about syntax, let's describe the process, because I find if you start thinking in syntax, you're more likely to make a mistake. If you start with some kind of English pseudocode, then you're more likely to be able to work through the logic in English and then replace that English with code. So inside of that loop, what are the English logic steps? Okay. Step 1. If it is even, what should we do? What's next?
And do the Fibonacci sequence.
Yeah, we need to something like this. When you determine that we need to update the values of prev and cur, how are we going to do this? Maybe this is where this mysterious temporary value might come in handy. But what is the new value of prev? So we can kind of start to logic. The new prev is the current cur. What is the value of the new cur? So new cur is going to be the old prev. Or I guess the current, we'll call it the current prev. Plus the current cur. Do we want to overwrite prev before we use it here? And we need to reference the current cur here. So is there any way to avoid using a temporary variable here to store one of these things? There is, but we're not going to worry about it for now. Because I think it makes more intuitive sense to just use the temporary variable. So we don't really need to initialize this to anything. We're going to initialize it in here. So as you do this, you'll recognize that to calculate the new cur, I need the current prev, so I don't want to overwrite prev before I use it. And if I overwrite the new cur, I need the current prev here and the current cur here. So I can't overwrite to the new cur because I'm going to access the current cur here. So you can't order these in such a way that you can overwrite one in advance, which means that we need to store one of them off. So depending on which one you do first, maybe current cur, this thing that we're going to need to calculate new prev, that can go in temp so we can access it later. So I think now we're starting to become ready to replace this thinking with code. Does this logic make sense? Just kind of thinking it through in English and then thinking about what are the updates here. I think that English really helps you to be able to see the logic and then make sure you don't make mistakes in your update logic. So what do we do to replace the first line with actual code?
If cur modulus of 2 is 0. Sum equals sum plus cur.
Make sure this is equals, so not single equals. Then we want to add to sum. That seems good. You don't necessarily need the curly braces around this because this if only has a single line. I highly recommend always doing it. If you ever need to come modify and you go, oh, I actually want to do two things under this if, you don't want to have to check whether or not this has more than one line. So I highly recommend curly braces. So that deals with these first two lines. That's why I also indented this. If you notice, whenever you write something in English, like if so, that's going to be inside of a logical if statement. So if you're writing things out in English, you can kind of start to do your indenting based on what's going to be inside of what control structure. All right, so this if statement will handle that. How do we update these values? How are we going to order these statements such that the update is successful? What's the first thing we should do? Yeah, we need to make sure we store what we need to access later in a temporary variable. So we can say, and I really should have written this over a little bit more. The current cur, we want to store that off. So that's already stored in cur. All right, what do we do next?
Cur equals cur plus 3.
Little shorthand there, should be fine. And finally,
3 equals 10.
do we see how the logic of the English from here maps onto the actual syntax that we want to use here? Anything else we need to do inside of this loop?
Maybe a print statement, just to make sure everything's running smoothly.
Yeah, you could print out sum and the current, yeah, you could absolutely do that to figure out, make sure that it's doing what it's supposed to. Are there any reasonable tests that we could write to do something like that for us? What tests would we use for something like this to determine whether or not it is performing to our expectations?
J-unit.
Some kind of JUnit test?
We could check if the sum is odd.
Yeah, if the sum is ever odd, that's a problem, right? Since if you're always adding even numbers, then after every iteration, the sum should be even. Sure, it's a reasonable test. So just start thinking about the kinds of tests like that that might be useful, because we'll be talking about that next week. But I think that this finishes our program. At the very end of this loop, we want to do something with sum. Print it out and paste it into Project Euler, see if it works. So this, of course, is all inside of that. And then we need one final close curly brace for the while. This can be in its own function. You could factor out quite a bit of this logic for the update and call that an update function. There are many improvements that we could make to this, but for now, it just has the logic. So this is an iterative solution to this problem. But as we know with recursion, whenever there's an iterative solution to something, there's also a recursive solution. So what needs to change about this? This is now your kind of your code base or your logic base. Once you have an iterative version of this, how can we produce a recursive version of this?
When you return if, wait, sorry. You would return if your threshold is reached
Yeah,
by your career. That's your first check.
so we need what parameters? So the function is going to be, we're going to call this something like fib. It's going to return an int. It's going to be whatever the current sum happens to be. The idea is every iteration of this loop should be a function call. So we're going to do some work. We're going to call it again as we update. And then as we hit that threshold, we're going to start going back up the recursive chain, carrying up the sum. Where we add to the sum, that's going to be what happens on the recursive way up. So I always think of recursion as something like Inception. You go into a deeper and deeper dream state, and you do some logic each time you do that, and eventually you hit your base case down here, and then you're going to go back up through all of the recursive layers and eventually have an answer from all of that work, from all of those different dream states. What do we notice about this recursive chain? We talked about a particular kind of exception that can be thrown if your recursion is too deep. That's a Stack Overflow exception. So rather than write this out, we just have a few minutes left. I want to go into an interesting case that's just good for you to know intuitively whenever you are solving something recursively. And that is that you have to know how deep this recursion is going to be. Because all of these functions, this is paired with this logic is paired with this logic, is paired with this logic, is paired with this logic, is paired with this logic. I did not draw that correctly. There we go. And you can imagine that this is kind of a timeline where we have the beginning of the program and the end of the program. And this is the same work until we identify the base case, and then we go back up. Does that make sense? Kind of recursively just thinking about the beginning of the program to the end of the program in terms of a timeline. In order to want to do something recursively, we need to know what this max depth is. So if we're looking to exceed 4 million on this, we need to know how deep 4 million is in the recursive chain. I would argue that that's a really annoying question to ask. You almost have to solve the problem to know whether or not it's worth doing this recursion at all. The question is there a way to prevent this from happening while still using recursion? And the answer is yes. It's called tail recursion, which is a subset of recursion itself, where you don't have to do this. You're actually going to embed this logic in the passing down here. So if we were going to make a function for this process, what would the parameters of that function be?
Even curve.
Yeah, so if you're gonna do this with regular recursion, you would have two parameters. And if we implement it this way, we're gonna get this kind of work, where everything that's happening here on the way down is the determining whether or not the current value is even, and then updating. And on the way back, we're gonna know what the total so far is, and we're ready to add the current value to that, and that's what's gonna be happening here. But do we notice that we don't really need to do that? We could pass that sum so far as an additional parameter on the way down the recursive chain. If we do this, if we actually add this to a third parameter and pass down the sum so far as part of that recursion, then is there any work to do on the way back up? No. Once we finish this and start the next level of our dream state, there's nothing to come back to. There's no further logic to come back to, which means that this function no longer needs to live on the stack.
Does that mean you just return sum as your base case?
Yeah. And once you reach your base case, you're done. You've calculated the sum and there's no work left to do. Which means that no matter how deep this recursion gets, you're never gonna see a Stack Overflow exception. You're never gonna crash your program. You can make this value as big as you want, and you will never run out of stack space. So I don't necessarily know time in this class will I ask you a tail recursion type question, but I just want to impart whatever wisdom I can whenever we're talking about recursion. As in if you don't have to do this, you will prevent a failure point in your program if you just pass an extra parameter that is the accumulator or the accumulation. You'll see this in functional programming languages. It's called an accumulator. It will be keeping track of the answers so far so that you can go as deep as you want without running out of stack space. Questions about that? All right, I will leave it as an exercise over the long weekend. If you want to do this recursively and or tail recursively, if you implement it recursively, try also implementing it tail recursively and see if there's a limit that gives you a Stack Overflow exception if you don't do it tail recursively, and then see if that limit goes away if you do implement it tail recursively. And I will tell you, it will go away. Java, the compiler, is smart enough to know, is this needed anymore? If it's not, get rid of it.
If we implement the tail recursion, do we get extra credit?
I don't see why not.
Thank you.
Thank you.
Thank you so much.
Already got the stack from my recursion.
Nice.
I have like, I have a missing edge case of zero mode, so
Mhm.
bang, and throw it out there. I was like, yeah, there you go.